I've just changed the locus a little. The RFLP locus is slightly different. There are actually two different RFLPs that are being analyzed simultaneously by the same probe. Correct? There is a site here called R2 and a site here called R3, and these sites can appear in this. Both of these sites can be RFLP. That's what we're analyzing. So we have this fragment, the C fragment, which is an 8 kb fragment in this example, analyzed by this probe. We're going to use the same probe in all of these individuals. In this individual, the allele B, R3 is the site that's missing. So when R3 is missing, you end up with a 6 kb fragment. When R2 is missing and R3 is missing, you end up with an 8 kb fragment. Now what happens if you're missing R2 but not R3? What are you going to see under those conditions? What size fragment would you see? If you're missing R2 but R3 is present, it's not shown over here. What would you expect? What size fragment would you see on a gel? 4. And so you wouldn't be able to detect the appearance or disappearance of the R2 unless you also have R3 missing. Right? So the analysis of R2 is dependent on R3 being absent. That's very important. Otherwise you can't detect. And you might have to develop a new probe that you would use. But under the conditions that I have laid out over here for you, you can analyze 3 different alleles under these conditions. Now what you notice is the parents are heterozygous, but they're heterozygous for different alleles now. The father is heterozygous CA allele. So in one case, he's got this configuration on one of the chromosomes. He's got this configuration at the locus, the RFLP locus. On the second chromosome, the second copy, the homologous chromosome, he's got this configuration. The mother is heterozygous, but not exactly the same as the father. The mother is heterozygous BA. She's got one allele of this type and one allele of this type. And now when you notice the son is AA, got the A allele from the father and the A allele from the mother. And notice the daughter is now a CB mutant, not a CC mutant like in the previous example. So slightly different. Irrespective, the daughter is still affected. In the mother's case, this B RFLP locus was linked to the mutant allele, very closely linked. In the father's case, it was the C allele that was linked to the mutant. And so when the B and the C came together, you became a mutant. Is this clear? There is a homework problem. I think it was in the practice exam homework problem, which is somewhat related to this, where I have a pedigree with 2 parents and then I think 8 children, and I have 2 different alleles. I think it's a cystic fibrosis gene question, where I discuss something that looks like this. There are 2 loci, 2 RFLPs, one on one side of the cystic fibrosis gene, one on the other side of the cystic fibrosis gene, and you're asked to determine how this happens and what's going on in the progeny, and carriers especially, as well as the effect. So pay attention. So when we look at these alleles, we've labeled them as this in this fashion. We can also label them with respect to the restriction sites. Now under these conditions, you have to pay attention to 2 different restriction sites, R2 and R3, because those are the ones that are appearing and disappearing. And so this father here is basically R2 minus R3 minus R2 plus R3 plus heterozygous, correct? C and the A. The mother is R2 plus R3 minus R2 plus R3 plus. She's a B and an A, and that's why she's an R2 plus R3 minus R2 plus R3 plus. This son here is AA, and so he is R2 plus R3 plus 1. plus R3 minus R2 plus R3. And so you realize under these conditions that the mutation is likely to be close to the R3 allele, not the R2. It's more likely that the mutation is going to be somewhere here, rather than it's kind of tells you can narrow things down in a sense. Okay, so you can use RFLPs to map genes. Once you know RFLPs, you can map the RFLPs across an entire chromosome or even the entire genome if you wish. And you can then analyze the patterns. So here is a pedigree of a family. The father here is affected, and then 3 of the children are affected. It's most likely this is a dominant pedigree, simply because you've got both generations and it's being passed on from one generation to the next. Can't be absolutely sure at this point. We need more generations to be sure. But it's possible that it's a dominant pedigree. Let's look at the RFLP patterns and see where the mutant lies with respect to 3 different RFLP loci on the chromosome. So, you can do this analysis. What you're looking for is a very simple correlation. All you're looking for is a pattern of RFLP markers that always go with the mutant phenotype and not with the individuals who are unaffected. So all you're trying to do is look for an RFLP pattern that is always present in all of the individuals that are mutated, 1, 2, 3, 4, but never in individuals who are unaffected. And that will give you an idea of that locus being either at or very close to the mutant gene that you are interested in. So we are looking at 3 different loci on the chromosome, locus 1, locus 2, locus 3. We know there is a mutation. And we want to know where this mutant gene lies, whether it lies next to locus 1, whether it lies next to locus 2, whether it lies next to locus 3. Because of linkage, if it lies next to locus 1, the RFLP locus 1 and the mutant phenotype should always go together, or almost always go together. If it lies close to locus 2, then it will be RFLP locus 2 and the mutant phenotype that will go together. If it lies at locus 3, it will be the third one, but not the first and the second. So it's a simple extension of what you already learned about linkage. If there are 2 loci that are linked, they tend to go together. That's all we're trying to find out. Is a particular RFLP locus always segregating with the mutant phenotype? And when you find that, then you can say the mutant gene lies at or close to this RFLP. So let's look at this pattern here. Some locus, let's imagine this is locus 1, right here. And we're looking at a pattern of restrictions, fragments, 1 kb and 9 kb. The father is heterozygous 1,9. Mother is homozygous 1,1. Notice how this band is darker than this band because she's homozygous. She has twice the number of copies of the 1 kb fragment. And then these children, some of them are 1,9, some of them are 1,1 because of segregation. You can get the 9 allele from the father or the 1 allele from the father. You always get the 1 allele from the mother. So you always have the 1 allele in all the children, and then some of the children have the 9 allele from the father, some of the children have the 1 allele from the father. Now, let's analyze this individual who's affected. This mother is affected. She's homozygous 1,1, right? So it could be that the father is heterozygous. It's possible, correct? If that's the case, and if the 1 allele is the one that's linked to the mutation, then this individual who's affected would have to be 1,1 homozygous, and it's not. Correct? This individual is 1,1 homozygous, this female, but she's not affected. So it's unlikely that this RFLP locus, the 1 kb fragment, is linked to the mutant gene. Correct? Because it's not correlated. It's not going exactly the way the mutant gene. It's segregating away from it. So it's likely that the mutant gene does not reside at or near this locus 1. Okay. Now, let's look at the second locus, this one. 2 bands, 5 and 3. That's the RFLP. You either have a 5-5 or a 5-3. So, once again, we analyze this pattern, looking for individuals that are affected. Now, this individual is affected, and he has a pattern 5-3. This individual is affected and is homozygous 3-3. This individual is affected and is homozygous 3. So it doesn't correlate. The mutant phenotype does not correlate with a particular restriction of RFLP pattern. So it's unlikely that locus 2 is linked to the mutant gene. Let's look at the third pattern. Okay. So here, this female is homozygous 8. This male is heterozygous 8-6. This male is heterozygous 8-6 and is affected. So imagine that an 8-6 is the key, and if you're heterozygous 8-6, you might be affected. Analyze this individual is affected, sure, 8-6. Analyze this individual is affected, 8-6, affected, 8-6. Everyone that's unaffected is homozygous 8. Everyone that's affected is a heterozygous 8-6. So now here you have a very strong correlation between a particular RFLP pattern and the phenotype that you are studying. And it's likely that this is a dominant phenotype because these individuals are all heterozygous and they're having this. Likely, can't be sure yet, but it's likely. But what you can see very clearly is that this locus 3, located here, is at or close to the mutant gene that you are interested in. And so that's how you would be able to identify a particular gene adjacent to a particular RFLP. Now this is of course a very simplified version of this. You can't get this information from a single pedigree. Usually you analyze over 100 different pedigrees from individuals who are affected. And you analyze these RFLP patterns, many different RFLP patterns. And then you'll be able to determine the identity of the locus variable, if it's a single gene trait or multi-gene trait, etc. So which RFLP pattern segregates specifically with all of the diseased individuals but not with the normal individuals? That's the key question you're asking when you're trying to correlate an RFLP pattern with a mutant phenotype. When you find it, you'll be able to tell. Now, sometimes you may not find it. It is entirely possible that you analyze all 3 RFLP loci and you find none of them are linked. That's also possible. So then you say, we analyze all of them, but these RFLP loci are not linked to the mutant phenotype. The mutant gene must be somewhere else. You're only analyzing a handful of loci using this method. You're not analyzing the entire genome, correct? So it's possible you may not find linkage. That's also entirely possible. So don't just expect to find linkage when you see something like this. It's possible or not. Luck does affect research results sometimes. Sometimes you pick a position to study, you're lucky, you hit the right jackpot, you find a linkage, and you can clone the gene. But it's also entirely possible that you won't find linkage, in which case you have to continue doing additional experiments until you do find it. There's an element of luck involved in research. Okay. Any questions on this? Yes? How do I know if it's linked or not? Well, because every time a particular pattern goes with a mutant phenotype, you're saying it's linked. Now, obviously, when you're doing it in real life, you have to analyze hundreds of individuals. Here, you're only analyzing 6 individuals, correct? But like I've always told you, the pedigrees I give you will be representative pedigrees of all 100 individuals will be analyzed. Correct? So for the class, it's just a representation of what's going on in real life. So you have to basically figure out. Here, it's obvious that these four individuals who are affected have a particular pattern that always goes together, and that's locus 2. You don't see that correlation with locus 2 or locus 1. Correct? That's all you have to do. Just simple correlation. One of the patterns has to match. Or if it doesn't match, you say they don't match. Right? If they're not linked. Up to you. But you have to try and see if there is a pattern that matches. That's all. No, it can be for recessive as well. Except in the recessive case, you wouldn't have two patterns. You have just one pattern. That's another way to do it. Like the previous example. Yeah. This is a recessive trait. Right? So again, you're looking for a correlation. Yeah. You can do this for a recessive or a dominant. It doesn't matter. Okay, so what we're doing basically is we're trying to map two genes. What do we do when we map two genes using classic Mendelian genetics? Because I'm going to take you back in a sense to before the midterm. You're performing a cross, okay, using a heterozygous individual. Right? When you're mapping something, you're doing a test cross between a heterozygous individual and a homozygous recessive. And you're going to look for the appearance of recombinants and the frequency of recombinants. That's the key, correct? The frequency of recombinants is basically an indication of distance between two loci based on recombination. So, let's imagine you have two genes E and W, that are required for wing development and bristle development. And so to map the distance between these two genes, you're going to take the two genes and you're going to need certain alleles of the two genes such that we can generate a heterozygous individual for both of these genes at each of these loci. And then we're going to look for recombinants. So, to measure distance between the two genes, you do a test cross, a double heterozygote, i.e. big W, little w, big T, little b, is crossed to a double homozygote recessive. Little w, big B, little b, a test cross, correct? That's what you do. Then you look for recombinants. So, here is a female, big W, big B, little w, little b, crossed to a male. And then, you're going to look for heterozygotes that will appear in this individual. So, the female will produce 4 kinds of gametes. You guys are really familiar with this. Big W, big B, little w, little b, big W, little b, little w, big B. The male will produce a single kind of gamete. And then you're going to analyze phenotypes. From the phenotypes, you're going to determine the genotypes, and you're going to determine the recombinant class versus the total, and you're going to determine the map distance. So, individuals with wings and bristles, individuals with no wings and no bristles, individuals with wings with no bristles, and individuals with no wings and bristles. And you count the project, 51, 43, 3, 4, and you say these two are the recombinant classes, and the map distance is 7 over the total. Correct? Very simple, very straightforward, classic mapping of two different loci. So, map distance is 7 over 101, which is 7 map units. Right? I mean, this is just a reiteration of what we studied before the midterm. That's what we do. Okay. So, to find the map distance between genes, we're using multiple alleles. And we're measuring the number of recombinants over the total individuals that you're analyzing across. And we're determining the distance. However, let's imagine a situation where you have another locus over here. This is the distance between the W and the B gene, 7 map units, the distance between the B and the R genes, 20 map units, etc., etc. You can map it using this recombination frequency. Now let's suppose you generate a new gene, gene C. That's what you want to study. All right? And you can map it using this classic method of crosses. Now, but what happens if gene C is difficult to study because the phenotype is very difficult to analyze correctly? Let's say the only way you can analyze the phenotype of a mutant gene C is by using an electron microscope. That's not trivial to analyze a particular phenotype using electron microscopy or whatever, some other technique, right? It's a difficult phenotype to study, but that's what interests you. And you want to map this gene now. You want to know where this gene lies on the chromosome. If you can't do it using a quick phenotype, maybe if you're lucky, there is an RFLP that is curated. And so you can say, okay, let's use an RFLP to study this. I can't use a phenotype I can observe with the naked eye. Maybe I can use an RFLP from these flies to study this particular and how it segregates. So there's the gene that you're interested in. And so you could study it using simple RFLP analysis. What is an RFLP? It's a locus, just like a gene. And it has different alleles. You can have a 7 kb and a 4 kb, or a 5 kb and a 2 kb. They're different fragments. Those fragments are indicative of 2 different alleles of the gene. So you just simply plug in the size of the alleles. The size of the bands on a gel is the equivalence of big B, little b. You can imagine big B as being a 1 kb band and little b being a 2 kb band. You can imagine big W being a 1 kb band or 7 kb band, little w being a 4 kb band. You can imagine big R being a 3 kb band, little r being a 9 kb band. So you can use RFLPs to map genes exactly the same way as you're using the appearance of particular phenotypes that we are using. So RFLPs are simply loci on a chromosome that you can use as alleles and markers. So you can use these as markers along the chromosome to map an unknown gene with respect to that. That's what I'm showing you with the pedigrees, and that's what you can also do in a classical cross in your software. So you just map them. Here is the big B, here is the little b. You have a 3 kb and a 2 kb. Here is the probe that you're going to use. And you're using this cut. Here is the gene. Let's imagine the wild type gene has a 2 kb fragment. The mutant gene gives you a 5 kb fragment. So when you're big B, you're 2 kb. When you're little b, you're 5 kb. When you're big B, you're 5 and 2. It's the same thing. Instead of looking at the bristles under the microscope, you're basically analyzing the appearance and disappearance of ants on a shell. That's the only difference, basically. No other difference. So you can map a gene with regards to this, and instead of looking under a microscope, you may not like looking under a microscope, maybe you prefer looking at gel pictures. And so instead of saying wings, no wings, bristles, no bristles, you can simply say 5 and 2 kb, 5 kb, etc. So you can use a different ability to map. So once again, right here, same cross as before. Instead of analyzing bristles, you're simply looking at bands on the gel. The bristle locus becomes an RFLP locus. It's a 5 kb and a 2 kb. If you are big W, big B, big B. If you're little b, sorry. I know why I do this. If you're big B, little b, that's what you are over here. You're basically a 5 kb and a 2 kb. If you're little b, you're 5 kb, 5 kb. If you're little b, you're 5 kb, 5 kb. You're big B, little b, 5 kb. Confusion? When you're doing an RFLP, you have to pay attention to the fact that even though this little b is a recessive allele from the male, you will detect it as a 5 kb band. because this little b over here is going to be a 5 kb band. That's going to come in. This big B is going to come in as a 2 kb band. So when you generate a heterozygous fly that has bristles, that heterozygous fly with bristles will have a 2 kb band. They'll also have the 5 kb band that was given by the father, the male. And so you'll see 2 bands, the 5 kb and the 2. But here, your little b homozygous, you only have a 5 kb band. Okay, questions on this? This is just another way of, yes, go ahead. If you're homozygous dominant, how would you get a homozygous dominant in a test cross? Right? You wouldn't, because you're always using the homozygous recessive as one parent. So you wouldn't see that. But you could get a homozygous dominant from a different cross, not a test cross. You just see one band of 2 kb. Right? Because of the location of the probe. Look where the probe is. Right. The probe is sitting only in the 2 kb band. It depends on the probe. I could have had a band that sat across. Then you get, for homozygous dominant, you get 2 and 3. For recessive, you get 5. And if you are heterozygous, you get 2, 3, and 5. Right. You get 3 bands. So we're talking about genetic polymorphisms. We talked about repeats and DNA fingerprints. We talked about RFLPs. We're now going to look at a different kind of variation called single nucleotide polymorphisms or SNPs. So a genetic polymorphism is basically a difference in DNA sequence between 2 individuals. And there can be differences between individuals, groups, population, whatever. That's the polymorphism. A genetic mutation is a change in the nucleotide sequence of the DNA molecule that results in a change in the phenotype. And genetic mutations are a subset of genetic polymorphisms. So polymorphisms are the encompassing term, and within it you will have mutations. So variation can be repeat heterogeneity or changes in nucleotide sequence. And then within this class, you have 2 classes. You have RFLPs and you also have SNPs. So I'm going to talk about SNPs now. It's a single nucleotide polymorphism. It's a source of variation in the genome. A single nucleotide change in DNA sequence at a particular location along your chromosome. And these are the most common and simplest form of variation that you see between individuals. So 90% of all human polymorphisms are basically SNPs. Most of their changes occur at the level of single nucleotide changes at one particular location. And there are 2 types of nucleotide substitutions that can happen. You can have something where an A or a G is converted to a C or a T. Or you can have a purine converting to a purine, or a pyrimidine converting to a pyrimidine, or you can have one where the purine gets converted to a purine. Don't worry about the terminology, transitions and transversions. Nobody uses them very often these days. Now, in theory, a single base can change to any of the other 3 bases. So an A can change to G or a C or a T. Correct? In theory, that's possible. What we observe at most SNPs is that if there is an A, it's likely that it will convert to one of the other 2. It's not that it always converts to one. It's more likely to convert to one or the other. So, but let's just assume it converts to any. Okay? But in theory, that's not true. All right. So let's imagine here is a sequence. Here is an individual with a sequence A, C, G, G, C, E, A, A. Here is another individual, same bit of DNA, and there is a single nucleotide change, A, T, G, G, C, E, A. This C has converted to a T. deletion or an addition, it's basically a substitution. You're changing a sequence position. So, instead of using restriction enzymes, you detect SNPs by either sequencing an PCR